In this video, we develop a finite element method for the membrane deflection problem. Recall that the equation of the membrane deflection is d squared u by dx squared plus d squared u by dy squared equals minus p over s. This can be thought of as arising from the following Tonti diagram. So we have the deflection, we have the slopes, and then the tension components, and the inflating pressure, plus the boundary conditions. The relationship between the deflection and the slopes is simply the gradient d by dx, d by dy, and what satisfies virtual work, the adjoint, is minus the divergence, which is the row vector minus d by dx minus d by dy. So to compute an approximate membrane deflection, we break up the region of the membrane into triangles. We call this the finite element mesh. We call each triangle a finite element, and the assembly of triangles the finite element mesh. Now, within each triangle, we approximate the deflection of the membrane by a plane. So a patchwork of these planes is going to approximate the full deflected shape of the membrane. So let's take a typical triangle with the vertex coordinates like this. And the deflection of this triangle is going to be a plane. So it's going to be a plane in three-dimensional space. And let the displacements of the joints 1, 2, and 3 be u1 superscript e for element, u2e and u3e. Since the deflection is being approximated by a plane, its equation is linear. U of xy can be written as a plus bx plus c1. At the vertices, the displacements must be u1e, u2e, u3e. So substituting this, we get these, and writing it in matrix form, we get an equation for the coefficients a, b, c in terms of the joint displacements u1e, u2e, u3e. Let's call this matrix M, and the joint displacements u sub e. So we get the coefficients a, b, c as m inverse u sub e. So the displacement function u of xy is 1xy times the coefficients. And we can write it like this, and we call this matrix that multiplies, it's a 1 by 3 matrix, and we call this the interpolation matrix n of xy. Now the slopes can be computed like this, and that matrix, not surprisingly, we call that B. So the slopes S equals B times the joint displacements UE. Now let's write an expression for virtual work using the Tonti diagram. But this time we'll distinguish real displacements. We'll use the letter U for real displacements and delta U for virtual displacements. So the internal virtual work is the virtual slopes transposed the real tension components. And if we substitute delta S equals B times delta UE, we get that. The external virtual work is the virtual displacements times the pressure. And if we substitute delta U equals N times delta UE, we get that. And while we do these integrals, it's helpful to recognize that the integral of x is simply the x coordinate of the centroid times the area, and the integral of y is simply the y coordinate of the centroid times area. And the x and y coordinates of the centroids are simply the average of the vertex coordinates. So if we substitute all of this, we get kind of a simplified expression for the external virtual work. Now if we set external virtual work equals internal virtual work, and recognize that this statement must be true for any virtual displacement, we get the following equation. The stiffness matrix Ke times U plus equals a load vector QE times the pressure P. So these are the element stiffness matrices. They're 3 by 3, and they can be assembled into the global stiffness matrix by the usual process. And the load vector, the element load vector, can be assembled into the global load vector, just as we assembled the thermal loads in assignment number 1. So simple FEA can be modified relatively in a straightforward way to solve the membrane deflection problem, and hence the torsional constant problem.